I mentioned at the end of the last video that the magnetic forces on a current carrying wire form the basis of what we talk about as an electric motor. So the idea is to take electricity and create motion. That's what a motor is, an electric motor, right? You take electricity and you somehow turn that into creating your wheels spinning so your car moves forward. How does that motion happen? Well, here we're going to have a very simple example. So we have a loop of wire. It's really a rectangle of wire, length L, width W, and I'm going to place it on a spinning axis so it can spin around this axis. So think of a flat piece of paper. I hold it in the middle and I can rotate it from that point. I place that in a magnetic field. In this case, you can see the magnetic field is going into the board here. Now I need to establish a current, the direction of current. I'm going to have the current going clockwise. So on the top, the current is going to the right. On the right, the current is going down. On the bottom, the current is going to the left. And to the left, the current is going up, right? So current is flowing around. Of course, I don't show a battery in here or anything like that. We're just going to pretend I've set this up so this current can flow in this direction. So let's look at, there are 4 lengths of wire here. Each has current flowing. Each has current flowing in those segments. So current is flowing in a magnetic field. So let's look at what happens to this wire. Well, first of all, let's look at the top. Current is flowing to the right. Fingers in the direction of the current. Push the current onto the magnetic field, which is into the board. My thumb is up. So this top wire feels a force upward. So the current in this top part of the wire is trying to pull the wire up. On the right-hand side, fingers in the direction of the current is down. Push the current out of the magnetic field. My thumb is pointing to the right. There's a force here on the right-hand side trying to push this loop to the right. On the bottom, fingers in the direction of the current, push the current out of the magnetic field. My thumb is going down. So there's a force on the bottom going downward. And not surprisingly, fingers in the direction of the current, push the current on the magnetic field. The left-hand side has a force to the left. So you can see that this loop of wire is getting pulled in all sorts of different directions, right? It's getting pulled to the left, to the right, to the top, and to the bottom. And if you actually calculated how much force there was, which again depends on, if you remember the previous equation, depends on the current, it depends on the magnetic field strength. The current in this loop of wire is always the same. The magnetic field throughout this loop of wire is always the same. So it depends on the length of the wire. Here the top and the bottom have the same length, so they would have the same force. The right and the left have the same length, so they would have the same force. So what really happens here is all of these forces cancel. As far as this loop is concerned, this loop is not pulled up or down to the right or to the left because all those forces cancel. Imagine a big loop, a solid, take some pipe and create this type of a loop and have 4 different people on different ends pulling. They all pull with the same force, or at least your opposite pulls with the same force. Therefore, the object isn't moving. Now let's flip this and look at it from the side. So I'm going to take this, imagine the piece of paper looks like this, and I'm going to take it and flip it like that. So the magnetic field, or sorry, flip it, piece of paper like this, I'm going to flip it like that. So the square, I'm going to turn to that direction. So rather than the magnetic field coming into the board, it's now going to the right. So we're seeing the loop from the side, right? Length L is going into the board and coming out of the board. Width W is shown here. Remember, it's rotating about this central pivot axis point. Here it looks like I had this square, but what if I had it tilted a little bit? So this top piece is a little bit further back than the bottom piece, so it's tilted back, like that. Well, you would still feel a force here, F top, would still pull up. F bottom would still pull down. So the net force on this object is 0. This object would not move up or down. However, this object would experience rotation, right? There's a torque here. Because this force does not go through the center of rotation. Basically, if I were to grab this end top and pull up, and grab this end and pull down, I would straighten, so if it looks like this, I would straighten the loop. I will cause the loop to rotate. So I'll cause the loop to rotate. That's motion. That's current in a magnetic field generating into motion. So as this spun, when it gets to the top, it's at an equilibrium. It's where it wants to be. But what I can do is change the direction of the current, and now this top piece will feel a force downward, the bottom piece will feel a force upward, and if I spin this, it's going to continue to spin around. And then I flip the current again, it'll spin around. And I flip the current again, it'll spin around. And what I've done is I've created a motor, a rotating piece of wire here, due to the fact that I have a current in a magnetic field. I do have to switch the current around every half turn, but there are ways you can do that with what are called brushes. It's fairly easy to do. And we create a rotating. Well, how much does this rotate? What is the torque? Well, torque, if you remember, is the force times the lever arm distance from the center of rotation. So here's the center of rotation. If this entire thing is length W, then this piece here is the width over 2, as is that piece, W over 2. And if you remember, the torque is maximum when the force and the lever arm are perpendicular to one another. It's 0 if the torque is parallel to the lever arm. So there's a sine theta that we have to worry about. So when theta is 0, there is no torque. When theta is 90 degrees, we get maximum torque. So you get torque from the top, which is equal to the force on the top times the lever arm, which is the width divided by 2 times the sine of the angle, plus the torque on the bottom, which is the same force, same magnitude, times the lever arm, which is the same, times the sine of the angle, which is the same. So you have this over 2 plus this over 2, basically the over 2's disappear, right? So you end up with force times width times sine theta. But we have an equation for force on a wire, right? Force is equal to I times L times B. So plugging that in, we end up with the torque, which is the current I times the length of that top and bottom piece of wire L, times the magnetic field strength B, times the width of the wire, W, times the sine of the angle shown here, the angle from the face of the loop compared to the magnetic field line. Well, length times width for a rectangle, you have length here, you have width there. Length times width is area. Right, so area is length times width. So I'm going to replace the length and the width with area A. So the torque on this loop depends on the current flowing through it. No current, no torque. It depends on area A. The bigger the loop, the more torque you get. It depends on the strength of the magnetic field. No magnetic field, no torque. And the angle of the orientation between this loop and the magnetic field. Now this is a single loop of wire. In most electric motors, you have multiple loops of wire. 100, 1,000 loops of wire. So if you have n loops of wire, each loop of wire gives you this torque. So you just multiply this by the number n. So the total torque of n loops of wire of area A is given by this equation. It depends on the number of loops you have, the current going through the wire, the area created in that rectangle, magnetic field strength, and the angle shown here. So if you want to know what the maximum torque is, that's when sine theta is equal to 1. And you can calculate what the maximum torque possible is for this electric motor. Now this rotation, electric motor rotation, is critical in creating a rotating system that then that torque, that spinning system, can be applied to a wheel or a gear or something along those lines, turning electricity into motion. But for electricity to turn into motion, you need a magnet. You need a magnetic field. Just having current doesn't do it. You need a magnetic current in the magnetic field to generate the torque necessary for this thing to start rotating.